Welcome to this 9-week course on computers, waves, and simulations. In the background, you see a nice scenery descriptive of nature. I'm an earth scientist, so we would like to understand how the earth works. And there are many phenomena like climate, weather, earthquakes, oceans, how they circulate, and so forth, that if you want to understand them, they require simulation technology. Now, what is simulation technology? Is the application of numerical methods to the partial differential equations that describes the phenomena that you're interested in. Now, this course will be, I call it a practical introduction to these numerical methods by taking the simplest possible equation that is time dependent, the wave equation, that's used in many fields, is important for many phenomena. And by taking that equation, we compare it, how we can solve it with different numerical methods. These methods are the finite difference method, the pseudospectral method, the finite element method, and a slight modification of the finite element method called the spectral element method. Now, who could you be? You might be a student who is interested in getting a kind of a practical introduction to numerical methods, and also learning a little bit how this is implemented in using a programming language. And for that, we actually use Python, which is, a very popular language, extremely useful. And also we make use of so-called Jupyter notebooks. That is also a fantastic concept where you can combine basically a document with graphs and interactive programming parts that you can run and get new results. You might also be a researcher that's interested in using a community code that simulates a physical or some other phenomenon, and it might be parallel and it runs on a large supercomputer. So we'd like to know what's under the hood. It's like opening the hood of a car to look inside the engine. What's the element that makes the car work? So that's very important to understand the benefits and the traps of these simulation codes. And that's basically what we would like to convey in this course. The fact that if you want to simulate real phenomenon, you need very big computers means also we will talk at least a little bit about what's the architecture of modern computing, parallel computing, and what are the programming paradigms that exist to bring realistic simulations onto a computer. It will be relatively brief, but again, that's very important to understand the fundamental concepts on how realistic problems can be solved. I'd also like to show you what this course is not. This is, while the course is quite mathematical, this is not a mathematical course. I'm not a mathematician, I'm an earth scientist, and would like to teach you or train these kind of techniques from a practical point of view, as mentioned before, in the sense that we'll basically take the partial differential equations, we show how you can turn them into a discrete approximate version, then you can turn into a computer code and run it. We're not going to spend much time in proving that these concepts are correct, but we will show concepts how to ensure that what you simulate on the computer actually produces an accurate result. So those are the fundamental concepts. And now let's get started in the first week with introducing some of the main concepts that are necessary before starting applying numerical methods to partial differential equations. If you're interested in a little more detail than what's covered here in this course, you're welcome to look at this textbook that has recently been published at Oxford University Press. So what will be covered in this first week? We first talk about discretization. If we want to simulate something, usually there's a spatial scales and the temporal scales involved, and we want to understand the concept of wavelengths. And that also implies that we need computational meshes on which to solve our partial differential equations. So we will briefly talk about computational meshes and grids. Furthermore, we need to distribute these meshes on computers. And if these meshes are very big, you need a computer that's actually parallel. And so we'll also cover some very fundamental aspects of parallel computing. Then we'll give a short introduction to the Python language and the Jupyter notebooks we use. And of course, this will be interactive. You will also be able to make use of these simulation codes that we will develop within the course and play around with them. So that's, in addition with some fundamental concepts, will be week 1. And then in the second week, we'll actually start learning about the first numerical method, the finite difference method, and apply it to the wave equation. Now let's get started.